Welcome to the Scientific Montessori Podcast, where we translate the latest academic research into Montessori-aligned practices and share insights to make parenting dramatically easier. This episode brings you the audio version of our article, Why Learn Mathematics Through Discovery. To explore more articles, visit scientificmontessori.com.
I want to talk about why learn mathematics through discovery. But first, I'd like to define mathematics. Galileo Galilei famously said, "The universe is written in the language of mathematics." What do you think?
Mathematics can be defined as the study of structure and pattern.
Does that mean it describes the universe?
Essentially, what we call mathematics is the correspondence of the universe's structures and patterns to symbols. If you don't map the universe to numerals, numbers, and mathematical symbols, but instead just speak in ordinary language and turn it into a story, it becomes mythology.
Is the mathematics that humanity has developed the same as the mathematics that describes the universe?
There are two kinds of mathematics. One is human mathematics, the mathematics we learn in education. The other is cosmic mathematics, the mathematics the universe has. The history of human mathematics is a history of corrections to human mathematics. We hypothesize maybe there's a law like this and verify it, but eventually it turns out to be wrong and gets corrected by later generations.
Like relativity theory to Newtonian mechanics.
That's physics. For a pure mathematics example, Euclidean geometry to non-Euclidean geometry.
Right.
The history of mathematical development is mostly like this. First, you have some illusion, like, isn't this the pattern? Then the next generation says, wait, that's wrong. It gets corrected, like Gauss or Euler. But some people hit the right answer from the start, like Pythagoras, discovering that triangles have certain properties, the Pythagorean theorem. For other people, the next generation, they can't deny it, it's too useful. Even ordinary children can calculate area with base times height divided by 2. But we couldn't use it with confidence if Pythagoras or earlier generations hadn't discovered the law, or if no one had verified it. However, even things used that way for a long time might still have errors. That's both the fascination and the terror of mathematics.
That's true. Is there a pattern to when corrections happen?
Usually corrections come through technological development. What I mean is, for example, when you want to see far into the universe, you build large telescopes, space telescopes. First, you have to think about how to launch them. You need mathematics and physics for the launch. Then you also need technology for seeing farther, and that uses mathematics and physics too. And then how to handle the data you get from it, what patterns to find from it. You need to answer propositions like whether the universe is round.
The shape of the universe was actually solved using mathematics and physics with the Poincare conjecture.
Right. And there are various unsolved problems that need proof, like Fermat's last theorem.
Like verifying whether the proof of the ABC conjecture is correct.
Right. And to solve these more efficiently, new mathematics is sometimes needed. And that new mathematics is actually undiscovered cosmic mathematical principles.
Like Edward Witten doing new mathematics while researching superstring theory.
Here's a spoiler for readers. That coordinate system you learned in education is called Cartesian coordinates because Descartes created it, and it's very convenient. When drawing graphs, you say x-axis, y-axis for 2 axes. For 3 axes, you add z-axis. This Cartesian coordinate system is not correct cosmically.
That's a what moment?
It doesn't work in the universe.
Since Earth is a sphere too, you can't express it. When you go to the edge, you have to come out the other side.
Right. Even on Earth, we were approximating calculations quite a lot to get answers. We were forcing it quite a lot, actually. GPS calculations, for example, approximating curves with straight lines, using the squeeze theorem and limits to cleverly handle complex differentiation. The calculations are incredibly difficult.
Right.
Since computers were invented, it's fine if the computational load is enormous. Or rather, computers were developed because of that computational load.
Right.
Being able to do all sorts of things with computers is a really great thing, but really, if there's a way to reduce computational load, that would be better.
Mathematical proofs sometimes use computers to brute force things, like the 4-color map problem. If it could be proven without computers, that would be beautiful.
Right. Computers would use less electricity too. Now with AI development, they're consuming enormous computational resources, and there's even talk of needing nuclear power. Electricity shortage is a problem. Data centers are running at like 100% capacity, constantly operating. Electricity becomes a problem. Then you're consuming fossil fuels. Why is this happening? It's because the mathematics is wrong. The underlying mathematics.
That's really true. Whether global environmental problems get solved depends on the evolution of mathematics.
Right now, we're calculating in extremely inefficient ways. With the cosmic approach, computational load becomes 1/3.
Is that the power of cosmic mathematics?
In other words, because we're calculating in Cartesian coordinates, computational load is 3 times what it would be cosmically. This is essentially an assumption. People think mathematics has no errors and is always correct. They feel mathematics never changes forever, or that it doesn't change because it's been proven.
So separate from whether something is proven or not, there's the discussion of whether it's efficient.
Right. We know it can be solved that way. For example, there's brute force giving random values, trying lots of random things when solving calculation problems, and if you hit the answer, lucky. Just repeating like, please let tomorrow be sunny. That method exists.
AI is a type of that too, generating images from random seed values, hoping something good comes out. Or when you want new materials with specific properties, you generate randomly and pick what's probabilistically likely. Same with shogi moves.
If you do that, eventually you'll solve it, brute forcing. But if you do that for every problem, it's game over. In the end, because it's proven isn't really a reason. The legitimacy of human mathematics is simply how much it matches cosmic mathematics. And the more it matches, the more you can predict the future. This is a bit of self-promotion, but Polymath School, which started in April 2025, defines intellectual that way and aims to be the most intellectual school.
Right.
Calculation layers inferences. Like the Japanese proverb, when the wind blows, the barrel maker profits. It's a saying about chains of unlikely cause and effect. You go through about 10 inference steps from wind blowing to the barrel maker profiting. Mathematics is about becoming able to layer inferences. There's all sorts of randomness. So people immediately start talking about chaos, saying we give up, we can't predict the future. But including that, you can still produce prediction accuracy. You can express it as probability.
That's how AI has been developing too.
Weather forecasting, too. It keeps evolving, using AI to predict more accurately. This is the Laplace's demon story. If you could accurately predict the state of all particles, you could always predict the next state.
The idea that the future is determined.
We're approaching that. In other words, cosmic mathematics is that direction. If you understood all of the universe's state and principles, you could predict the universe.
That's where quantum physics comes in.
The idea that things are probabilistically determined, so the future is uncertain, 2 states superimposed. But that's human understanding. It's not that the universe decided superposition is uncertain.
This discussion is getting complicated.
Simply put, as an efficiency of representing information, superposition is good, so you could say the universe uses it. An interesting point here relates to the power of folktales from the previous issue. For example, in The Crane's Return of a Favor, a crane secretly weaves cloth disguised as a young woman, and children naturally understand superposition. The crane in the weaving room is in a superposition state of daughter and crane.
Same with the big wicker basket in Tongue Cut Sparrow.
Richard P. Feynman said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." Elon Musk said, quantum mechanics is the most difficult. Jeff Bezos said, I was going to become a physicist, but gave up at quantum mechanics. Meanwhile, in Japan, 5-year-olds readily accept it. Entanglement, the Urashima effect. There must be many more folktales if you look. And it's not because some great scholar thought them up. They've been passed down among farmers since ancient times, and people listen because they're interesting.
So children are given all sorts of patterns, and much later they can discover on their own, oh, this is that pattern.
Straw millionaire is also the law of conservation of energy. Straw equals lotus leaf equals miso equals sword equals millionaire.
But straw does not equal millionaire, right? Isn't that mathematically incorrect?
That's being tainted by human mathematics. Buckminster Fuller said mathematics must include time, gravity, and temperature. In cosmic mathematics that includes time, the equality holds.
It's hard to escape human mathematics. Please properly teach me about how calculations become 1/3 without Cartesian coordinates.
You'll discover that yourself. That's what learning through discovery means.
Thank you for listening to the Scientific Montessori podcast. We hope today's episode helped you see how research and Montessori principles can make parenting simpler and more meaningful. For more articles and resources, visit scientificmontessori.com and join us again next time.